Welcome to this video. We're going to learn about another type of problem involving simple harmonic motion. Now, in the last lesson, we learned about period for a spring and mass system and about period for a pendulum. Here's the new problem. A 2.5 kilogram frictionless block is attached to the end of a horizontal spring, it should say, with spring constant or stiffness 175 newtons per meter. The system is pulled back and released. How many cycles does the system make in 3.4 seconds? Now, when we see 3.4 seconds, we're thinking, oh, this is a time, right? So we start to write down the equation with time. And it's period, capital T, equals little t over number, where little t is the time it takes to complete this number of cycles. So what's 3.4 seconds? What's 3.4? Is that capital T or is it little t? Well, they didn't say that 3.4 is the time for one cycle. In fact, what they're saying is find the number that corresponds to this interval. So 3.4 is little t, right? It's little t. So we're looking for how many cycles, which means we're looking for this and we're given this. But before we can calculate the answer for number, we need to first find capital T, the period. So how do we do that? Well, we use this equation for period. We know both the mass and the spring constant, so we can proceed by simply writing out the answer, right? Plugging in the values, that is. 2.5 is the mass, the spring constant is 175, and we calculate this to get 0.75 seconds. So we plug it in down on this part, right, for the other equation. We know little t is 3.4, and we're looking for number. Now we have to isolate the number, which means we need it in the numerator, and right now it's in the denominator. So how do we get it out of the denominator? We multiply both sides by the number of cycles, and then they cancel out. So now we have number in the numerator, and we need to get rid of this 0.75, which is multiplied with it. So what do? We divide both sides by 0.75. And this gives the final answer of 4.5. And you might want to say, oh, 4.5 seconds, but that's wrong. We just found the number of cycles, and so it doesn't have units. We don't even write 4.5 cycles. We just say 4.5 is the number of cycles. So we're going to complete numbers 1 through 7. Now, before we do, I want to show you one other thing, another type of problem, and one other fact. We know that amplitude doesn't change how long it takes to do one cycle, right? That's something we've studied already. So if I pull this pendulum on the left, this mass, if I pull this down a small amount, small amplitude from the center, and I pull this one down a big amount, then they'll have the exact same period, right? So let me run the simulation and try and get them both going. Okay, they're both going. And we're going to move at full speed. Now it's hard to see because they're not synced up. They're kind of synced. But they actually have the exact same period. It takes this one the same time to make one cycle as it takes this one. So which one has a faster average velocity or average speed? The one that is moving a farther distance has a larger average speed, even though the period is the same. So this one is going much slower on average because of its small amplitude. So here's what we can say. Amplitude impacts the average speed of the mass. And that's going to be true for pendulums too. Not only is this true for masses and springs, but also pendulums. So the average speed equation is distance over time, but we're going to use an S for distance, and I'm going to rewrite the equation. Now, in one period, when the interval is 1 period, capital T, this equation says we travel 4 amplitudes. Is that true? Let's go back to the simulation. Okay, here we are. I've got the simulation up. I'm going to push this thing up, and look at where I'm measuring my equilibrium. I'm measuring it from the bottom of the spring. So I push it up 1 amplitude, right? From the equilibrium line up to here, that's 1 amplitude. And now I'm going to let it go. 1 cycle. It goes 1 amplitude down to the middle. Here's the second amplitude to the very bottom. Here's a third amplitude back to the middle. and a fourth amplitude back to where we started. And now, whoops, so it goes down, up a third amplitude, and a fourth to get back to where we started. So that's one full cycle, and we travel 4 amplitudes in one cycle. So that's where this equation comes from. Now I want you to take a moment and try to figure out why is there a 4 in the numerator, right? And explain this. We've already discussed it, but I want you to explain it in your own words. Now there's another thing to point out, which is that when the block is released from rest, and when it's released from rest, we just let it go. The amplitude is simply the initial displacement. If you pull it back 2 meters and you let it go, it's never going to go farther than 2 meters from the center. The block can never go farther than where it is pulled from, or what we'll say is from where it starts. Can't go farther than where it starts. So here's a problem. I want you to take a moment to read over the problem. We've got a frictionless block, a horizontal spring. Oh, it says horizontal that time. We pull back 0.50 meters and we release from rest. That means 0.50 is your amplitude. The block makes one cycle, one oscillation, in 1.6 seconds. To find the average speed, you use the equation from above, right? 4 times amplitude over the period, time for one cycle. And so you calculate to get 1.3 meters per second. Now you'll use this equation in some of the problems, but we could make it complicated by having you calculate t. Maybe we give you mass and the spring constant, and you have to find t from the equation. Or maybe we give you the frequency, and you have to find t that way. So you're going to have to go back to your equations, and there's a key posted. Work out numbers 9 through 19.